Hello everyone, welcome back to Bytes of CSE. So in this lecture, we'll be talking about the Bayes theorem. Now this is very important a theorem when you are dealing with data science or machine learning. And I'm sure you have come across this particular formula because if you haven't, you wouldn't have been here. So Bayes theorem is based on conditional probability, which tries to find out the probability of an event given that a condition has been satisfied. So it is more that the extended form of Bayes' theorem is very important while tackling those sums which you generally encounter, all those real life situations that you might come across. So I will be trying to explain this Bayes theorem to you using an example. So let's get started. So imagine you're watching a cricket match with your friend, and just after the batter has pitched the ball high, your friend pauses the video and asks you, now what is the probability that the batter hits a six? Now, this is kind of uh, the example that fits into the conditional probability. Now you have seen that the batter has pitched the ball up high, and now you would like to know the probability that that this ball will hit a 6. Now when your friend asks you a question like this, you will immediately think of the probabilities that might happen or the events that might happen when a batter pitches the ball high. So what are these events? Number 1 is the batter hits a 6. Next, the ball just falls just before the boundary line. It dips before the boundary line and it becomes a 4, or the ball drops somewhere not even near the boundary, and there's a fielder and the batsman or the batter just manages to get a few runs, maybe 1, 2 or 3, and the final probability is the ball goes straight into the hands of a fielder and the batsman gets out. So depending on this, so these are the event, like the event of hitting a 6 is is a fraction which is the event of a sixer. Now this E stands for event. This is for this particular space constraint. I have used E for denoting event. Sixer plus the next probability was a 4 run or a boundary. The next probability was less than 4 runs, and the final probability was the event of getting out. Now, if you are trying to, your friend has asked about the probability of this batter hitting a 6 when he pitches the ball high. Now, this depends on the kind of the batter he is. Like an opening batsman or a good batsman like Rohit Sharma or Mahendra Singh Dhoni hitting a 6, the probability of them hitting a 6 can't be anywhere near to a tail ender, like a bowler who's batting right now. So naturally, you will be needing the statistics of that particular batsman. So now, the conditional probability that, now this P stands for probability, and this notation actually stands like the probability of a sixer given that this has already happened. Like H denotes that the ball has been hit high, it has been pitched high. So this has already happened, and now we are trying to find out what is the probability that this is going to be a sixer. Now first of all, then we have to try to find out the probability that the batsman can at all hit a 6, like he has sufficient timing, good timing, or the perfect placing that it actually hits the 6. So we need to consider that. Then we need to consider that now this might seem very stupid because this particular notation means what is the probability of hitting or pitching the ball high if one needs to strike a sixer. Now this might seem very stupid for all you cricket enthusiasts because of course a ball can't hit a 6 without you pitching up the ball. But this is not so stupid if we consider other phenomena. So obviously this probability in this case will be 1, of course. But anyway, we need to consider this probability. Why? I will be tackling another example where you will be understanding that why you need to consider this particular phenomena. And now you have to consider, like, this particular summation comes here. Like, what is the probability of a sixer given that is a sixer has been a sixer has been struck, and the probability that the ball has been pitched high, plus a ball has been pitched, a boundary has been hit, and what was the probability that the person, like, maybe in some cases the person, the batter has hit a boundary. Whenever the batter hits a boundary, he pitches the ball high. So you have to consider this kind of probability, and of course the probability that the batsman can at all has good placement ability to hit a boundary. Next is the probability that there has been less than 4 runs and the person has pitched the ball high. And what is at all the probability, like, the person takes short runs, because there are different kinds of players. Like, a few players likes to take short runs, a few players prefers to go for a big hit, right? So you have to consider that probability. And next you will consider the probability where whenever the batsman has gone out, so what was the probability, or what was the event that the person has, like, pitched the ball high and he has gone out, into, of course, the probability of the person getting out. Now let me consider this example. Now this is the kind of questions which you will be getting a lot. Like, let's go through this example. Like, suppose a disease has an incidence rate of 0.1%, which means that 1 in every 1,000 person will have this disease. A test has been devised to detect the disease. The test does not produce false negative, which means that probably the person has got the disease, but your test fails to recognize that. And the false positive rate is 5%. Now, if you have gone through the video I have made on the confusion matrix, you know that false positive means that the test has shown that yes, the person has the disease, but that is wrong. That is, the person has not got the disease, yet the test result shows that he has got the disease. So that is known as a false positive. Suppose a randomly selected person takes the test and tests positive. What is the probability that this person actually has the disease? Now let us try to understand it using a bar line. Like, say this bar, this entire bar, it depicts, or it represents the entire population. So it says that 0.1% of the entire population can get the disease. So let that be this red bar. This denotes that there is, like, this is the diseased population, and it says that while it does not have false negative, it does have a false positive rate of 5%. So let this orange bar depict, like, these are those people who will be detected as positive, but they actually don't have the disease, right? Now we have to find out that a person has been selected randomly. Now when you randomly select a person can be selected from here, or from here. Now it says that that person has been selected, and that person takes the test and he has been tested positive. So that means we have actually selected a person from this part of the population. Now we have to find out that what is the probability that the person actually has the disease. So what is the probability that that chosen person is chosen from this particular segment? So now we will, now everything has to be calculated with respect to the entire population. Now this is your formula which I had shown previously when I started the lecture. And now if we now we are to find out what is the probability of the person being diseased given the test has been positive. So this has already happened, and now we are trying to find out that what is the probability that this is true. So first of all, we will need to consider that what is the probability of the disease happening. So that is, what is the probability of this with respect to the entire population into what is the probability that the person has the disease and will be tested as positive. This means that the person already has disease. This has already happened. So the left part indicates that this has happened, and the right part indicates that what is the probability that this might come true. Okay. So what is the probability that the person has the disease and he will be tested positive? And that divided by what are the kind of events that we might go through in this entire scenario. So it might be that the person has been tested positive, but the person has no disease, so that is also another probability. And of course, this has to be considered. So this plus the probability of no disease, and this probability of no disease is the probability of the entire population having no disease. We are not considering only this part, we are considering the entire population, that the particular person has no disease, into the person has been tested positive, but the person has no disease but has been tested positive. So if we consider this now, the probability of the disease, it says it's 0.1%. If we convert that to decimal, it will be, we'll shift 2 more points to the right hand side, which becomes 0.01, and the probability of this probability that the person has disease and will be tested as positive, that is 1, because it says that the test does not produce false negative. Say if the test had produced false negative, and say that had been 5%, so in that case this probability of being there is a disease and the person being tested positive would have been 100% minus 5%, that is 95%, or in other words it would have been 0.95. Okay, because 5% of the people will be positive, but they will not be detected as positive. Now since it says that they produce no false negatives, this will be equals to 1. This particular probability is 1, and that divided by probability of disease, which is 0.0001 into 1, plus probability of no disease, which is 100% minus 0.1%, that is 99.9%, not having the disease. And when we shift that to the decimal thing, it becomes 0.999, and the probability of that person being tested positive, even if the person has no disease, that is your false positive rate, which is 5%. When we convert that to decimal, it becomes 0.05, and this is approximately 0.0196. Now you will be going through this kind of problems mostly, and that was all for today. Hope it clears your doubt regarding probability, like base theorem and conditional probability. So that's all for today. Thank you.